Area of a polar curve.
Let's start by reviewing the area of a sector. To find the area of a region in a polar coordinate system, we use sectors instead of rectangles. As a reminder, a sector is a part of a circle, and the area of a sector with central angle theta is given by, well, first we need theta over 2 pi, which represents the fraction that corresponds to that part of the entire circle. So we have, if theta is the central angle, then the fraction of the entire circle is theta out of 2 pi. And we take that fraction and multiply it times the area of an entire circle, which is pi r squared. So the area of that part of the circle, if we multiply these two, ends up looking like 1/2 r squared theta. So notice that the pi's cancel out. So 1/2 r squared theta is the area of a sector, provided we have the angle theta given in radians. Now let's move on to approximating area using sectors. For a curve r equals f of theta, the area of each approximating sector is given by a sub k equals 1/2 times r sub k squared delta theta. Let's look at this graph over here. We have our polar curve r equals f of theta, and we're interested in the area between the two angles. Let's say theta equals some alpha and theta equals beta. Here we're using 4 sectors to approximate the area. So we'll go ahead and say that the area of each sector is a sub 1, a sub 2, a sub 3, and a sub 4. And so each of those areas is found by using the area of a sector formula, where the radius of each sector is found by using that halfway radius here. So that's like my R1. And then delta theta is dividing this total angle by 4. So each of these has an equal angle measurement here. So similar to like how we have a delta x when we're talking about using rectangles to approximate area in functions in Cartesian coordinates in x and y. So we can see that there's this amount of error associated with using a finite number of sectors. But if we increase the number of sectors that we use, so here in this first picture we're using 4, and then now we're doubling it to 8 sectors, we can see that we have a better approximation with less error. So we have our Riemann sums that approximate the region. That's a finite number, an n number of sectors. And if we take the limit as n approaches infinity, so if we increase the number of sectors and head towards infinity, then we're going to get to an integral that finds the exact area that we are looking for between two angles given a polar curve. Here we're going to look at the formula for finding area using polar coordinates. The area of the region between the origin and r equals f of theta from theta equals alpha to theta equals beta is given by the integral from theta equals alpha to beta of 1/2 r squared d theta. And note, as you go from alpha to beta, the curve must be traversed exactly once. In this example, we want to shade the region enclosed by the cardioid r equals 2 times the quantity 1 plus cosine theta from theta equals 0 to theta equals pi, and find its area. So here the polar curve is graphed, and the region enclosed by the polar curve from theta to pi is going to be the part on the top of the x-axis. So we're looking at shading the region from theta equals 0 to theta equals pi. So theta equals 0 is on the positive x-axis, and then pi is on the negative x-axis. And so we are extending from 0 to pi, moving along our polar curve. So this is the region that we want to find the area of. And what we're going to do is use this area formula up here. So we're looking at a is equal to the integral from 0 to pi, and then we have 1/2 the radius. Well, the radius is given by the polar curve. R equals 2 times the quantity 1 plus cosine theta. So we have 2 times 1 plus cosine theta. All of that is going to get squared d theta. So this is the integral that I need to evaluate to find the area. So let's go ahead and simplify it a bit. So here we're going to go ahead and have 0 to pi of 1/2 times 4 times 1 plus cosine theta squared d theta. So the 2 gets squared and the 1 plus cosine theta gets squared. 1/2 times 4 is 2, and we can pull that 2 out to the front. So 2 times the integral from 0 to pi of 1 plus 2 cosine theta plus cosine squared theta d theta. So I'm distributing out 1 plus cosine theta times 1 plus cosine theta. The first two terms in the integrand have a general antiderivative, but cosine squared theta we'll need to use the power reducing formula on. So we have 2 times the integral from 0 to pi of 1 plus 2 cosine theta plus 1/2 plus 1/2 cosine of 2 theta d theta. Combining 1 and 1/2 as 3/2, we get to 2 times the integral from 0 to pi of 3/2 plus 2 cosine theta plus 1/2 cosine of 2 theta d theta. After making some room here now, I have 2 times 3/2 theta plus 2 sine theta, and then here I'm going to have 1/4 sine of 2 theta. So here, remember the inside 2 theta, we're going to have an extra 1/2 come out of that from the antiderivative. And then this is evaluated from 0 to pi. So let's go ahead and plug in pi. So we have 3/2 pi plus 2 sine of pi plus 1/4 sine of 2 pi minus, now thankfully if we plug 0 into each of these we are going to get 0. Sine of 0 is 0. So this is just minus 0 there. And in fact, sine of pi and sine of 2 pi, those are also 0. So what we really have left here, so this one is 0, this one is 0. We just have 2 times 3/2 pi, which is 3 pi. So before moving on, I just want to recap that what we've done here in finding this number of 3 pi, that represents the area between the angles 0 and pi and the polar curve and the pole. So starting at the angle 0, we are moving in a counterclockwise direction, collecting area in the form of sectors. So we're going in this counterclockwise direction, and we're collecting, of course, these really, really thin sectors as I move around and head from that starting angle of 0 to this angle of pi. In this next example, we'll just set up the integral needed to find the area of the shaded region. With the given polar curve, r equals the square root of theta. So we can see this looks like a bit of a spiral, but we're only being asked to find the area of the shaded region, and that's the part here that's on the left side of the y-axis. So we need to figure out what angles to use for our area formula. So the area extends from theta is equal to pi over 2, and then we're going all the way around down here to this angle of 3 pi over 2. So we're going to go ahead now and set up our area formula as the integral from pi over 2 to 3 pi over 2 of 1/2 times my radius, but that is my polar curve, r equals radical theta, so we have radical theta squared d theta. And so we'll actually just clean this up a little bit. We can pull the 1/2 to the front, and then on this one, the square root of theta squared is just theta. So a pretty simple integral. But once again, before moving on, I want to reiterate how we are collecting area. So we're starting at this angle of pi over 2, and we're collecting the area of these very thin sectors as I move around in that counterclockwise direction until I get to 3 pi over 2. In this example, I want to set up an integral needed to find the area inside one petal of the rose curve r equals 4 sine of 3 theta. So this rose curve has 3 petals. We want to find the area inside of one petal. So here, let's say we want to find the area of the petal that's over here in quadrant 1. Well, we need to be precise about our limits of integration here. Where does this polar curve extend from? From what angle to what angle? So we need to look for this angle here, which kind of looks like theta equals 0. But then we also need to find this other angle here. And we're kind of unsure what that value is. So theta equals, I don't know. So what we have to do is find what are called the polar zeros. I have to figure out what angle takes me back to the pole, to the origin. So to do that, I'm going to need to set my curve equal to 0. So I need to solve when does 4 sine of 3 theta equal 0. So I can divide both sides by 4. I have sine of 3 theta is equal to 0. So how do I solve this type of trig equation? Well, let's just think about what angles do I plug into sine to get out 0. So in other words, maybe think about this problem for a second as sine of some x value equals 0. Instead of 3 theta, let's just make it x for a second. What angles do I plug in to get out 0? Whoops. All right, well, 0 is one of them, so x would be equal to 0. Also pi, and then 2 pi, 3 pi, and so on. Also, the negative multiples of pi. So negative pi, negative 2 pi, negative 3 pi, and so on. So we'll just stick with maybe this list for now. But again, the problem wasn't solve sine x equals 0. It was solve sine 3 theta equals 0. So what we can do is replace this x with 3 theta. So 3 theta is equal to 0 pi, 2 pi, 3 pi, and so on. And then we can solve for theta. So ultimately we want to solve for theta. So we'll divide both sides by 3, divide all of these answers by 3. So we end up with theta is equal to 0, pi over 3, and then 2 pi over 3, and pi, and then there are a lot more answers here. So what we did though was we found the polar zeros. What angles do I plug in to this polar curve that send me back to the origin? Well, 0 is one of them, and it looked like 0 was one of them, but now we can see this other angle here is theta equals pi over 3. And we found some more values, right? 2 pi over 3 and pi. So what those are these angles over here that trap the next petal in. So this is 2 pi over 3, and then the next one extends to theta equals pi, right? And then there are more answers, and that would be what finds the bounds of the next petal. So we have enough though. I mean, we have what we were trying to find, these limits of integration for our area formula. So let's go ahead and set up the integral. So our area is going to be the integral from 0 to pi over 3 of 1/2 times r squared, so 4 sine of 3 theta squared d theta. And so we can kind of clean this up a little bit. The 4 would get squared, that's 16. 16 times 1/2 is 8. We can pull the 8 to the front. So 8, the integral from 0 to pi over 3, and then we'd have sine squared 3 theta d theta. And the integration on that would require the power reducing formula.
On this example, I want to set up the integral or integrals needed to find the area of the region that lies inside r equals 3 cosine theta and outside r equals 2 minus cosine theta. The additional challenge here is that we have to draw the graphs of the polar equations. Since this was covered in another lesson, I'm not going to spend too much time on it here. Let's start with a plane. The graph of r equals 3 cosine theta is a circle that's going to be on the right side right here with a diameter of 3. Here is that graph, and if we started by substituting in 0, we'd see that we would start right over here, and then it would move in this counterclockwise direction. The other equation, r equals 2 minus cosine theta, there is a 1 in front of that cosine, so this value of A is greater than B. So this is going to create that dimpled limacon. And to graph this, I would just go ahead and plug in the quadrantal angles, 0, pi over 2, pi, 3 pi over 2, and then go ahead and create that dimpled limacon. All right, I tried my best here. This is a dimpled limacon, and the values were at 0. We go 1 unit towards 0, 2 units towards pi over 2, 3 units towards pi, and then 2 units down towards 3 pi over 2. So this is a rough sketch of what this looks like. And so the direction of motion is also in that counterclockwise direction. And now we want to find the area that's inside the circle. R equals 3 cosine theta was the circle. So I want to be inside the circle, but outside the dimpled limacon. So if I want to be outside of the dimpled limacon and inside the circle, we're talking about this right side region over here. I've gone ahead and shaded the region we're interested in finding. Hopefully we can recognize that this region has symmetry over the horizontal axis here. So I can go ahead and find the area of this portion in quadrant 1 and then double it, and that would give me the total area that I'm looking for. So in other words, I can go ahead and attempt to find just this top part. I've gone ahead and shaded it, and now let's try to figure out how to find the area of it. When it comes to finding polar area, we want to start at the angle 0 and think about collecting area as I move in a counterclockwise direction. So if I go ahead and start creating these little sectors extending all the way to the boundary of the circle, r equals 3 cosine theta, I'm collecting too much area. So I have all of this extra piece here that's still inside of the dimpled limacon that I want to get rid of. So what I'm going to have to do is sort of an outer minus inner situation. I'm going to find that total amount of area all the way extending to the boundary of the circle, but then I'm going to carve out this little inside part here. But I need to stop at this point of intersection. So it's all very similar. It should be sounding similar to when we did this in x and y. So when I had some function, let's say f of x, and some function g of x, and I wanted to find the area between those two curves, well, what I needed to do is find, again, their points of intersection, like A and B, and then we ended up saying it was top minus bottom, and the reason is because we found the area underneath f of x all the way to the x-axis, and then we subtracted the area underneath g of x to the x-axis. So that became f of x minus g of x, and that's top minus bottom. So all very similar, except that we're going to do that outer radius and then minus the inner radius that's happening here. So we do need that point of intersection, and so we're going to set our two polar curves equal to each other. We're going to set 3 cosine theta equal to 2 minus cosine theta. I'm going to add the cosine theta to the left side, so 4 cosine theta is equal to 2. And so cosine theta is equal to 1/2. I'm dividing both sides by 4. Now I want to think about what angle do I substitute into cosine to get out 1/2. And this is a quadrant 1 angle I'm looking for. So here theta is going to be pi over 3. So pi over 3 is this angle where we can see that these two polar graphs intersect. So what we're going to do is we're going to start at 0. I'm going to sort of do this the long way, and then I'm going to shorten it. So we're going to go ahead and set up our area. It's 1/2 the integral from 0 to pi over 3 of r squared. So first, I'm going to find too much area. I'm going to go all the way to the function 3 cosine theta to the circle. That's r. So 3 cosine theta squared d theta. So what I have found with this integral setup is I have found all of this area here, all the way up to pi over 3, but that's too much. So I need to subtract. I'm going to carve out this little piece right here. So I'm going to move it over a bit for some space. So I'm going to have minus 1/2 the integral from 0 to pi over 3. And then we're going to stop when we get to the dimpled limacon. So that function r is 2 minus cosine theta squared d theta. I rearranged to give us more space. All right, these both have a 1/2 in common, so I can go ahead and factor out the 1/2. And then I have these two integrals, 0 to pi over 3 of, let's write this as 9 cosine squared theta d theta, and then minus, again, I pulled out the 1/2, the integral from 0 to pi over 3. I'm going to leave this as 2 minus cosine theta quantity squared d theta. If I were solving, I would have to expand this out, but I'm just going to leave it. And so because these have the same limits of integration, I can go ahead and combine these to be one integral where I subtract the integrands. So this is 1/2 the integral from 0 to pi over 3 of 9 cosine squared theta minus the quantity 2 minus cosine theta squared, all d theta. So this tells me the area in quadrant 1, but then we needed to double it. So we need to be really careful here. I'm going to go ahead and just multiply everything by 2. So all of these, if I multiply them by 2, would give me the actual area set up for the region I was trying to find. So basically 2 times 1/2 cancels. So I would say that my area is finally just the 0 to pi over 3 of 9 cosine squared theta minus the quantity 2 minus cosine theta squared, all d theta. So don't forget to make sure the right amount of parentheses are involved. We include the differential d theta, the correct limits of integration. So even though it's a setup problem, there are a lot of places to potentially make a small mistake. In this example, I want to set up the integral or integrals needed to find the area of the region shared by the polar curves r equals 2 and r equals 3 plus 2 cosine theta. In this one, we are given the graphs. We just need to know which one is which. So r equals 2 is the circle centered at the origin with a radius of 2. And then 3 plus 2 cosine theta is the dimpled limacon. So we could have generated them as we did the previous one, knowing that we would substitute in the quadrantal angles, especially to help us with this second one here. So we want to find the area of the region shared by these polar curves. So what do they have in common, right? What's their region of overlap is another way of putting it. So what do they have in common is this middle part right here. So we're looking at what region is shared by both of them. So this portion over here is inside the circle but outside the dimpled limacon. This region over here is inside the dimpled limacon but outside the circle. So if we're talking about shared by both, that's the region of intersection right here. So where they overlap. I've gone ahead and highlighted the region here. Hopefully we can identify, just like with the last one, that there is some symmetry that we can use to our advantage. We can go ahead and find just the area on the top half and then double it. So there's symmetry over the horizontal axis here. I've gone ahead and shaded the region we're going to focus on, finding the area of, and then we'll double that region. To find the area, we're going to start at the angle 0, and we're going to think about creating those sectors. So I start by really just hitting the circle r equals 2 all the way up until a point of intersection. So what we're going to need to do is find that point of intersection, because that's where I'm actually going to switch off. And as I continue to collect area using sectors, after that point of intersection, I'm going to go ahead and be on the other function, the dimpled limacon. So we really need to find this point of intersection here. We're going to set the two functions equal to each other. 2 equal to 3 plus 2 cosine theta. First, I'm going to subtract the 3. So I'm going to have -1 equals 2 cosine theta. Divide by 2, so -1/2 equals cosine theta. We can see that we're over here in quadrant 2. So the angle in quadrant 2 that I substitute into cosine to get out -1/2 is 2 pi over 3. And there are definitely more solutions to this equation. I mean, we can see over here that these graphs do intersect again, in quadrant 3, and that's because, the next solution to this equation is 4 pi over 3. So we can definitely go ahead and find the other point of intersection, but if we're using symmetry, then we don't need it. So this one would be 2 pi over 3, and just for fun, this one is 4 pi over 3. So that's basically where we're going to switch off between the two functions. So we're going to need to set up two integrals here. I'm going to start with the area equals 1/2 the integral from 0 to 2 pi over 3. So we went from 0 all the way to 2 pi over 3 on which function? R equals 2. This circle here was R equals 2. And it's always a good habit to label our graphs. I didn't do that earlier. We just verbally said it, but so that we don't forget which one's which. So first we're hitting R equals 2. So that's our R, 2. So we're going to have 2 squared d theta. And then plus, because we're going to keep going, we're going to keep adding the area from 2 pi over 3 all the way until, okay, well, what angle's over here? This angle is pi. So we're going to have plus 1/2 the integral from 2 pi over 3 to pi of 3 plus 2 cosine theta squared d theta. We have two separate integrals and we needed both integrals. So this first integral gives us the area that's from 0 to 2 pi over 3 on the circle. The second integral gives us the area on the dimpled limacon from 2 pi over 3 all the way to pi. But now we need to double both of those. So basically I'm just going to go ahead and sneak a little 2 in front of each of these, 2 times 2 times, which will just make these be 1. So we're going to have 0 to 2 pi over 3 of just 4 d theta plus the integral from 2 pi over 3 to pi. And I am going to leave the quantity 3 plus 2 cosine theta squared d theta. Since I'm not solving, I'm just setting up, I'm not going to worry about distributing. In this example, we can see we have no graph, so we're going to have to graph. We want to set up the integral or integrals needed to find the area inside the inner loop of the polar curve r equals 1 minus 2 cosine theta. Well, yes, we have to graph, but there's a little bit of a hint because we want to find the area inside the inner loop, so that tells us this polar equation has a graph with an inner loop because it's an inner loop limacon. The value of A is less than the value of B, so it's going to create that hole in the heart, so it's going to create an inner loop limacon. And so to graph this, I'm going to go ahead and plug in my quadrantal angles to help me generate the graph. So if I substitute in 0, I'm going to get 1 minus 2 cosine 0. Cosine of 0 is 1, so 1 minus 2 is negative 1. If I substitute in pi over 2, I'm going to have 1 minus 2 cosine of pi over 2 is 0, so I'm just going to get 1. If I substitute in pi, 1 minus 2 cosine pi, cosine of pi, this is negative 1. So it's going to be 1 plus 2, or 3. And then 3 pi over 2, that's going to give me 1 minus 2 cosine 3 pi over 2, which is 0. So 1 minus 0 is just 1. Let's go ahead and take those now and draw our graph. At the angle 0, we're going to go away from 0 because this is a directed distance. So the angle 0 is this way, but I'm going to go the opposite direction, 1 unit in the opposite direction over here. And that's where I'm going to go ahead and plot my point. And then at pi over 2, I'm going to go 1 unit towards pi over 2. So pi over 2 is straight up. If I go 1 unit towards, I'm going to be right here. At pi, pi's over here on the left, I'm going to go 3 units towards pi over 2 because that's a positive directed distance. So I'm going to be over here. And at 3 pi over 2, I'm going to go towards 3 pi over 2, 1 unit. All right, so now I'm going to go ahead and attempt to sketch my graph. So remember, when I started at an angle of 0, I'm over here 1 unit away from 0. And then what I really need to know is which way do I start going? I know I'm going to create my little inner loop here, but am I going to go in a clockwise direction or a counterclockwise direction? So another angle that we could plug in to help us determine direction here, because it's unclear, is how about we plug in something like pi over 4. So if I substitute in pi over 4, so r of pi over 4, that's 1 minus 2 cosine of pi over 4. That's 1 minus 2 rad 2 over 2. Those guys cancel. 1 minus rad 2, that's about, because rad 2 is 1.414, that's about negative 0.414. So when I go to the angle pi over 4, so the angle pi over 4 is right here, I'm going to go away from that because it's negative 0.414. So I'm going to be about right here. I'm going to approximate that. So basically the direction of motion, whoops, I don't want to be dotted anymore. My direction of motion here is going to be in that clockwise direction, at least right now for this inner loop that we're creating. Now remember, from here we substituted in pi over 2 and got out 1. So this is going to keep going over here. And then we're going to go ahead and keep, this is going to be a little tricky, it's not going to be perfect. We're going to keep going out all the way to pi. So here's my continued direction of motion. And then we're going to go ahead and keep going around to that 3 pi over 2, heading towards 1. And then we're going to head back to the pole, to the origin 0, 0. And then we're going to finish out over here to complete that inner loop. So there's my direction of motion in there. So it's important to pay attention to the way that we constructed this because we want to find the area that was inside this little inner loop right here. All right, so how did we start this motion? So we typically think, okay, the angle 0, and we go to the right, but our angle 0 started this direction. And so when we start to plug in bigger angles, so even though we are substituting in angles, 0, pi over 6, pi over 4, pi over 3, just thinking about the nice angles, we are heading to negative directed distances. So I'm going to have my first angle here, and then I'm going to go around all the way until, well, what angle, right? So what actually takes us back to the pole? So what we need to do is actually find the polar zeros, because I need to figure out what angle finally gets me back to the pole, to the point 0, 0. So I need an r value of 0. I need to solve 0 is equal to 1 minus 2 cosine theta. So I'm going to subtract the 1. Negative 1 equals 2 cosine theta. Divide by negative 2, so 1/2 equals cosine theta. And that angle is going to be theta is equal to pi over 3. There's obviously lots of answers, but I'm going to stick to just the one in quadrant 1. So at an angle of pi over 3 is about right here, at an angle of pi over 3, that, it turns out, is when I head back to the pole. So it's like angle 0, and then pi over 6, pi over 4 was right here, and it turns out pi over 3 gets me back to the 0, 0 location. So why does that help? I mean, what are we going to do with that? Well, that's going to help me with my limits of integration. To find the area of this little inner loop, I'm going to go ahead and use symmetry. I'm going to start by just finding the area of this little bottom portion. Let me use a different color. This little bottom portion, and then double it. So our area is going to be, at first anyways, 1/2 the integral from 0 to pi over 3. So again, that's going this direction. 0 to pi over 3 of 1 minus 2 cosine theta squared d theta. That gives me this little bottom piece, and then we're going to double it. So if we multiply by 2, the 2 and the 1/2 cancel. So the area of that entire inner loop is just 0 to pi over 3, 1 minus 2 cosine theta quantity squared d theta.
In this example, I want to set up the integral or integrals needed to find the area of the region that lies inside the circle r equals 1 and outside the cardioid r equals 1 minus cosine theta. Let's start by shading the region we're trying to find the area of. We want to be inside the circle, r equals 1. That's the circle centered at the origin with radius 1, so I want to be inside that circle, but I want to be outside of the cardioid. So I want to be the region that's outside of this cardioid. So I'm going to need to erase part of this circle. So I don't want any part that's inside the cardioid. So this region here is what I want to find the area of.
This one's pretty similar to a previous example, so we'll do this one without using symmetry first, and then show what happens when we use symmetry.
So let's go ahead and get started thinking about this one. We're going to go ahead and set up two integrals here. First, I'm going to find the area of the semicircle between negative pi over 2 and pi over 2. So down here is negative pi over 2, and up here is pi over 2. So first I'm going to find the area of the semicircle here. So the right side of the circle of radius 1, so that's extending like from negative pi over 2 to pi over 2. We're thinking about essentially cutting it up into sectors like this.
Just be careful here and don't set it up from 3 pi over 2 to pi over 2. Remember, limits of integration need to go from small to big.
So the first integral I'm going to set up here is the integral from negative pi over 2 to pi over 2 of 1/2 times the radius, well the radius is just 1, the radius squared d theta. So that's finding the area of that semicircle, the right side of this unit circle. But then I need to carve out, or I need to take away a portion of that. So I'm going to need to take away this little region here. And so the way that's going to be found is I'm going to subtract another integral. I'm going to subtract the integral from, again, negative pi over 2 to pi over 2. So I'm starting from down here and collecting those little sectors. Negative pi over 2 to pi over 2 of 1/2 the radius of the cardioid, 1 minus cosine theta squared d theta. So again, the first integral finds the area of the full semicircle, and then the second one carves out these two little pieces here. Now, since these do have the same limits of integration, we can go ahead and combine them together to be one integral. So we can say negative pi over 2 to pi over 2 of the first integrand, so 1/2, and that's really it, because times 1 squared, it's just 1/2, and then minus 1/2, 1 minus cosine theta squared d theta. And I can factor a 1/2 out of both of these if I want. So we're looking at 1/2 the integral from negative pi over 2 to pi over 2 of 1 minus the quantity 1 minus cosine theta squared d theta. So that's the setup of the integral, or one way to express it, because what you might have also been thinking is there's some symmetry involved in this problem. So another way that we could have done it, another option, so I'll come down here and put or, what we could have done was found just the area in quadrant 1, so from 0 to pi over 2, and then doubled it. So it's still going to have this same integrand here, but the limits of integration are going to change. They're going to go from 0 to pi over 2 of that 1 minus cosine theta, all as a quantity squared d theta. But what's happening is we're going to double that. So it's going to be 2 times that 1/2 in front. And so, of course, the 2 times 1/2 cancels. So we can just find the integral from 0 to pi over 2 of that same integrand as before, and that's going to find the same area because we're able to use symmetry. In this last area example, we're going to set up the integrals needed to find the area of the region shared by the circles r equals 1 and r equals 2 sine theta. So coming over here to the diagram, we have this orange circle is the r equals 2 sine theta polar equation, and the blue circle is r equals 1. So that's the circle centered at the origin with radius 1. So we're trying to find the area shared by the circles, or the area that basically looks like a little eyeball. It's this region of overlap here. So in order to find this area, let's think about starting at the angle 0. So if we think about starting at 0 and then moving in a counterclockwise direction to start collecting area, the first function we're going to be collecting our area from is the orange circle, r equals 2 sine theta. So if we kind of think about collecting these little sectors, so first we are on the orange function, r equals 2 sine theta, right up until this point of intersection here. So we are going to need to find that point of intersection. So let's start our problem here. So our problem is going to look like the integral from 0 to, well, whatever this angle point of intersection is. But then we're going to have 1/2 the function 2 sine theta squared d theta. So that's going to find the area of this little portion right here that I've started to sort of sketch out. But again, I need this point of intersection, this angle. So to find that, we're going to have to set the two functions equal to each other. When does 2 sine theta equal 1? Well, I'll divide by 2 and instead think about when does sine theta equal 1/2? And so between 0 and 2 pi, when does sine theta equal 1/2? Well, that's pi over 6 and 5 pi over 6. And basically that checks out with our graph. We can see this looks like about pi over 6 here, and then there's this other point of intersection here, and that one is 5 pi over 6. So we have our missing limit of integration over here for this first integral. That's going to be pi over 6. So this first integral is going to find this little tiny area right here, but then I have to keep going. And now, as I continue on past pi over 6, the area I'm going to be collecting is on the function r equals 1. So I can kind of keep going. And you know what? I'm actually going to stop at the angle pi over 2. So I'm going to go ahead and set up an integral that finds the rest of this little area here from pi over 6 to pi over 2. So we're going to have plus the integral from pi over 6 to pi over 2 of 1/2. Our r value this time is just 1, so 1 squared d theta. Now, why did I stop right there? Well, because I recognize that there's symmetry. So these two integrals are going to find half of the area I'm looking for, sort of half of this eyeball shape. And so what I can do is just go ahead and double this. So I can go ahead and I'm just going to sneak a 2 in front of both of these pieces here.
So now these two integrals will find the area shared by these two circles. In this example, we want to set up the integral or integrals needed to find the area shared by x squared plus y squared equals 2 and the quantity x minus 1 squared plus y squared equals 1. Notice that the graphs are given, but my equations are provided in rectangular form. So the circle x squared plus y squared equals 2 is the one that is centered at the origin with the radius of the square root of 2. So we have x squared plus y squared equals r squared. So the radius is the square root of 2. And then quantity x minus 1 squared plus y equals 1 is a circle with the center 1, 0. So that is this smaller circle with the center 1, 0 with a radius of 1. So the other purple equation is the x minus 1 squared plus y squared equals 1. Now, even though these are provided in rectangular form, that doesn't mean we have to use rectangular form to find the area shared by these two circles. Let's go ahead and shade that area. Here is that region shaded, and if we were to try to do this in terms of like a top minus bottom situation, we would have to solve these equations for y to be a function of x, and then notice that they switch off. So I would go from 0 to what looks like 1, and then 1 to the square root of 2, and then the integration on that might not be that easy. So it's definitely something to think about, whether it'd be easier to do this in terms of rectangular versus polar. But let's just take a moment to think about how easy it is to turn these two equations into polar equations because they're both circles. So here, as long as we know that the radius is radical 2, the polar equation for this circle is just r equals rad 2. And then this smaller circle is located on the right side of this horizontal axis here, and the diameter is 2, so we're looking at this being r equals 2 cosine theta. So pretty straightforward in terms of writing these in polar form. And let's think about what it would look like to set up our polar equations. So now, if I think about the angle 0, I can go ahead and create my sectors. At first, just hitting the circle r equals rad 2. Now we would need to find the point of intersection, because after that point of intersection, we would then be on the smaller circle r equals 2 cosine theta. So we are going to go ahead and move forward with doing this in terms of polar. I'm going to set these two functions equal to each other. Radical 2 is equal to 2 cosine theta. Divide by 2, so I get the square root of 2 over 2 equals cosine theta. And then theta must be equal to pi over 4. So let's go ahead and recognize how that does make sense. An angle of pi over 4 right there, because we can see that point of intersection at 1, 1, and we think about tangent of pi over 4 is equal to 1. So that does check out. That is the angle. So if we were to set up our area here, again, from 0 to pi over 4, so area is going to be 1/2 the integral from 0 to pi over 4 on the circle r equals the square root of 2. Let me make this look a little neater. The square root of 2 squared d theta, and then plus 1/2 the integral from pi over 4 to pi over 2. So now we're going from pi over 4 all the way to straight up is going to be pi over 2. And then the circle there is my 2 cosine theta squared d theta. So what have we found? We've found just the area of the top. So let's see, this first part here and then the second part here. But we need to double that. So we're going to multiply both of those by 2. And that's going to give me the area. So 0 to pi over 4, the square root of 2 squared is 2 d theta. So that's the first integral, and then the integral from pi over 4 to pi over 2. Let's do this 4 cosine squared theta d theta. So these two combined, this is going to represent the area of the region that we're trying to find. Before moving on, I do just want to mention, if we really wanted to do this in terms of x's and y's, then we'd want to, again, think about splitting it up here and doing a top minus bottom situation. This side from 0 to 1, we're actually on the purple equation, so this equation here, I'd have to solve this for y. So in order to do that, I would subtract this quantity, x minus 1 squared, and then take the square root. So this portion right here, the top part of this circle, is going to be y equals the square root of 1 minus the quantity x minus 1 squared. And then the bottom part of the circle is the negative version of that. And so I would do the integral from 0 to 1 of top minus bottom, or I could think about just doubling the top because I can see the symmetry involved. And then the second integral would be from 1 to the square root of 2, and then top minus bottom here, I'd have to solve this equation. So x squared plus y squared equals 2. The top of this is y equals the square root of 2 minus x squared. And then the bottom, this piece, is y equals negative the square root of 2 minus x squared. So I could do the same thing. So just to kind of briefly talk about that, that's definitely more of a review from previous sections, so we could do it, but this was good practice for recognizing what the equation of a circle is in polar and then using that to find area instead.